Okay, so previously we went through the derivation, or a partial derivation. Apparently I can't write and talk at the same time. Previously we went through a partial derivation of Broyden's method, and today we're going to code it up from scratch in Python. Broyden's method, and we're going to be testing it on the Rosenbrock function, which is, I guess, sort of a standard, as it says right here on Wikipedia, a standard performance test function. It's got a minimum. Well, you can see it's of this form: a minus x quantity a minus x squared times b times quantity plus b times quantity y minus x squared quantity squared. And the standard is to have a be equal to 1 and b equal to 100. And when those constants are set to those values, at the point 1, 1, x and y equal to 1, this function will evaluate to 0. And it's a difficult function to find the minimum of, because you've got this long, very low slope valley. And so somewhere around here is the minimum. It's easy to get down into the valley, but once you're there, it's hard to navigate your way over to the minimum. So that's what we're going to be doing. To review, Broyden's method has a few basic steps, and those steps are, of course, you need some vector-valued function. That's the primary thing, and we'll talk about that in a moment, because the Rosenbrock function, as it's given here, is a multivariable function, but it's only got one output. It doesn't have multiple outputs. So you need a vector-valued function that you're looking for the roots of, the zeros of, and you start with some guess of x, and you evaluate your function at that x vector, and assuming that your function doesn't evaluate to 0 right away, and if it did, you're either a very lucky guesser, or well, you really don't need Broyden's method in that case. But based on that new x and that new f, you will calculate a new Jacobian, a new matrix of partial derivatives, and you will use that to treat your function as though it is a linear transformation, and based on doing that, you will calculate a new x, and you'll go through all these steps. So rather than doing things in NumPy, we're going to be doing things in JAX NumPy, and there are two principal reasons for that. The first is that JAX NumPy, JAX can automatically calculate gradients and Jacobians for you. So very convenient. We won't have to make the user of our Broyden's method function enter their own Jacobian. So that's reason one. And reason two is without some modifications, even with Broyden's method, converging takes quite a few iterations. And so we're going to use just-in-time compilation to make this, even with thousands of iterations, to make this a pretty quick and painless convergence process. Right, so let's import JAX, and let's import JAX NumPy as JNP. And if you're used to NumPy, everything that you put NP such and such after, or many things, you can just do the exact same syntax and just add a J in front. There are some differences apparently between JAX NumPy and NumPy. I mean, apart from all the things that JAX can do, there are some conflicting. One more thing. Let's see. JAX 64-bit configure. The default for JAX is to have The default for JAX is to have 32-bit precision, and we'd like to prevent rounding error and get there a little bit more quickly. I know it's in here somewhere. Config. Maybe that's how there's only 4. Oh, no, it's not in here. Wrong spot. 64-bit. JAX. 64-bit precision. I don't want configure, I want config. I don't remember this particular bit of code, so I'm hoping to steal it from somewhere. Is this where I just was? Yes, it is. So it must be the other one. Okay. Oh, this is the same place. Ah, here we go. All right. There's that little bit. That'll just set that'll give us a little bit more precision. Hopefully, maybe keep us from wandering down a blind alley, or maybe not. Who can say? So, absolute first thing. Let's get our function. Let's get our function in here before we go too much further. So our Rosenbrock function. Rosenbrock. All right, and let's scroll down a little bit. So let's define it. Define Rosenbrock. We'll make Rosenbrock a function of a single vector, which I'll call input. And we'll unpack it just for clarity so everybody knows what's going on. X will be input, will be the first entry input, and Y will be the second entry in the vector, in the input vector, whatever. And Python, of course, indexes from 0, which is why this is the first and this is the second. And then we'll return 1 minus x squared plus 100 times y minus x squared. Well, that's not how you square something. There we go. That's how you square something. And we should probably run this too. Okay, and we can test it out if we want, because Rosenbrock should evaluate to 0 at the point 1, 1 with these constants. Let's just, already we're making mistakes. So x, let's define our vector. X is equal to jnp.array, just like numpy. 1, 1, and there we go. Warning. JAX is used for machine learning, and so it's used to doing some pretty intensive stuff. So it's expecting we're going to be wanting to do some really demanding calculations. We're not going to be using JAX to its full potential, and so it's saying, are you sure you want to do this with no GPU? You'll be here a while. Okay. But the point is, we have our output down here of 0. So, and that's what we wanted. Our Rosenbrock function is working fine. Okay. All right. Now that we've done that, let's clear that out of the way, actually. Let's start to write our Broyden logic. So let's define a function. Broyden. And let's see. So what do we need? What do we need for our Broyden function? We need some function that we're optimizing, and we need inputs. So those are the principal things. And there are some other things we'll use too, Broyden, and we'll just call that function x. So, and then yeah, a few other things, but we'll just start here. So right out of the gate, we are, since this is an iterable thing, we are going to make a loop, but let's get our starting Jacobian. That's kind of the first order of business. So we'll call the what we'll do is we'll have Jack's numpy get the functional form of the Jacobian, which is true for the whole, true over the whole function, and then we'll evaluate it at one place at whatever our x is, and that's what we'll invert, and that will be our starting inverse Jacobian that we will then update through Broyden's method. So let's say Jack is equal to Jack's dot Jacobian. It's right there. Jack's dot Jacobian of our function. And I suppose there might be a time where we would want to let our user supply their own Jacobian. So in the spirit of that, we'll have an option to have it in there, but we'll have the default be none. So Jacobian, I shouldn't call these, I'll call this JC, and I'll call this optional supplyable Jacobian Jack none. So that makes it the default. If Jack is equal to none. So that's just saying if they don't supply us one, let's make this an is none, else Jack. So all we're saying here is if they give us a Jacobian, if they don't give us a Jacobian, calculate one. If the Jacobian is not none, which means they gave us a Jacobian, then let's use it. That's all we're saying here. And then let's evaluate it. So J is going to be whatever Jacobian function we've got, evaluated at the vector x, the specific vector that we were given. And then lastly, let's get our matrix inverse. So we'll say jinv is equal to jnp.linaug. Again, this is just like using numpy, and in this particular instance, linaug.j. A very small thing, but one that tied me up for a little while. If you are the x vector that we're supplying, make sure that they are floats and not integers, because Python will complain at you for trying to do that with these Jacobians, or particularly with J inverse for some reason. Okay, so at this point, we theoretically have our inverse Jacobian that is the starting seed for Broyden's method. I'm just going to shift enter and make sure there's not some syntax error. Okay, no obvious syntax error. Maybe a logical error in here somewhere. Let's see, and let's also evaluate our function. So we'll say f is func of x, and I think at this point we're ready to begin. So let's have let's just start our logic. For at the beginning, I'm just going to hard code some number, and then we'll include some logic. For I in range 10, we're just going to go with short ways to make sure things are working properly. For I in range 10, the first thing that we should be doing, well, we have an option here. We could check right away if we're meeting the condition that we want to be meeting, which is our function evaluating to 0. Presumably, our first guess isn't going to be right, so we could save that to the end. And if we do and it runs for one iteration, and after a good guess, a perfect guess, that no big deal. So the first thing I think we can do is we can get our new x. So if you remember from last video, our x new is equal to x minus our inverse Jacobian, Jn, matrix multiplied, oh, that's not how we do it, matrix multiplied by our function, our last value of the function. That's it. That's our x new. We also could just not have this x term here, in which case that would be equivalent to x new minus x. We'd be calculating delta x. You can kind of go either way. If we went that way, we'd end up having to calculate x new at some later time. If we go this way, we'll end up having to calculate delta x. So either way, it's 2 lines. Unless you want to be more baroque and more compact, but right now I'm just looking to write down some code that makes sense. So we've got our x new. That's the first step. Now let's evaluate our function at x new. So we'll go f new is equal to func of x new. All right. And we'll come back and add some things in later. But at this point, we have the things that we need to update our inverse Jacobian. We have our, well, actually, we're missing one thing. I'm going to say b because that's a term I saw used for the difference between the x new and x. B is equal to x new minus x. B is the same thing as delta x. Okay, and now we really do have all the things that we need to update our Jacobian, our inverse Jacobian. I'm going to use the Sherman-Morrison formula directly, and I'm not going to adapt it or reduce it down. As a reminder, Sherman-Morrison looks like such. And so I'm actually going to make a u vector and a v vector. I'm going to leave a inverse as j inverse. I won't get a new symbol for that. But our u is going to be equal to f new. Almost. F new as is will come out if we were to ask for the shape of f new, it would give us a little parentheses, some length, some number representing the length of f new, a comma, and then a blank space. So it sort of it's a vector, but it's not treated as though it has it's just treated as a row, but not some object that has a number of rows and a number of columns, even though it does as we understand it. So let's reshape it. So J and P, reshape f new. So that f new is what we want to be reshaping. Oh, not reshape. I don't know how to reshape something, but we can reshape. So we'll reshape it to have a length that is whatever the length of its, it has the same length as its last index, and it'll have or it's that number of rows, and it'll have a width of 1. So there, we've reshaped f new, and we've given it a new name. And then again, if you remember from before, our v vector for Broyden's method was b divided by b transpose b, which is to say b divided by the square of its norm. But we need to do the same thing here. We'll go j and p dot reshape. I could include that term outside or inside, but we'll make it the same shape. We'll make it however long it is, and then add one dimension to it outside. All right, and just like that, we're good to go. Plug everything into the Sherman-Morrison formula, and so let's do that. So here's our Sherman-Morrison formula. So I won't bother to call this like j inverse 2 or something. I'll just keep it j inv, which was equivalent to a inverse in this formula. is equal to jinv minus jinv matrix multiplied with u matrix multiplied with v transpose matrix multiplied with jinv divided by 1 plus v transpose matrix multiplied with jinv. Let me space things out just a little bit. And let me move this over because I'm sure that's behind my camera. So I'll switch things around. Okay. V transpose times jinv, we're almost there, matrix multiplied by u. All right, that's it. As a check, since we're actually dividing and not multiplying by an inverse, all this should evaluate to a scalar. And when we think, well, u is a column vector, a is a matrix, we multiply u by a, we get another column vector, and then that column vector times a row vector results in a scalar. So that all works. Not that I need to be double checking Sherman and Morrison, but it never hurts to look at these things and make sure that they make sense. So here we go. We've got our new inverse. Let's run this. Make sure there's again no syntax errors. There's always, well, I won't say there's always something, but it wouldn't shock me if something gets turned up as we go forward. Maybe you, the viewer, have already spotted something. If so, I award you 2 points. Okay, now we've got our new J inverse, and when we loop through again, that J inverse will go in here and get us a new x new. Let's update our f and our x that will go in that expression. So we'll say f is equal to f new, and we'll say x is equal to x new. Okay, and just like that, in this very compact space, what, 1, 2, 3, 4, 5, space, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines, we've theoretically accomplished what it took us an hour to talk about in the last video, which is kind of amazing that there's that much background in this little compact piece of code. Not quite done with our function. For a start, we need to return something. So let's return x first, and let's also return f, and let's return I. In fact, let's return them in a different order than that. Let's x, f, I. And so when we get our function out, even if we don't print things out inside the function, which, spoiler alert, we will be doing, we'll know what iteration we ended on. Okay, so should we plunge right in? Let's give ourselves some tools to manage the process. Let's add some number of iterations so that we can control things. We can always make it crazy high if we need to, and I have in the past. So max it, we'll say our default max it is 500, and let's also epsilon, or just eps for short, 1e to the minus 12. Let's also have an exit condition. Let's have some condition where, if we set this to run, heaven forbid, for 10,000 iterations, and it converges on iteration 150, we don't need to run that extra 9,850 iterations. So let's have an exit condition. And the exit condition that I think I'm going to use is if our if the length of our f vector is sufficiently small, or the norm, in other words, of our f vector is sufficiently small, we can be done. So let's add that as a condition, and I'll put that at the end. So if f, let's add it up a little higher. In fact, let's add it right at the beginning. If jnp dot linalg dot norm of f is if this is less than our tolerance value. Let's add a tolerance parameter to tol equal to epsilon as a default. Is less than our tolerance value. Then we will break. We'll exit our loop, and then whatever x and f are and I are will be returned. Let's also print all these things so we can see them as we update. So we'll say x and f, and let's get J inverse too. J inverse. And so we want x, we want our f value, and we want our J inverse. J inverse. All right. And x, f, J inverse. Okay. Yep. So we'll just be printing these things right along. Let's put J inverse on its own line, because it's a matrix, and it'll be shifted off if we print things on the same line. Okay, so we've got that. Let's make this conditional too. If we'll put some condition up in the top. If verbose equals true, then and we'll make that the default. Verbose equals true. All right. Just like this, we've got pretty much everything we need. You know, never was a ship that sailed smoothly, or you know, there's some saying like that. That's not it. Ah, there we go. If verbose not respecting the logical syntax of Python, -2 points. Oh, and I need to update this as well. And whammo. Okay, at least no syntax problems again. Maybe there's a logic error in here somewhere. All right, let's try this out. And then if it works, we'll add some constraints. So yeah, we've got everything going here. Let's move this. Let's move this down so we can look at it, because that might be desirable. Okay, so we've got our Rosenbrock function. Now, as I think I said before, let's take a look again at the Rosenbrock function, because again, this is just a surface. It's not a vector valued function. We only get one number out of this. We put two numbers in, which are represented by the coordinates on this plane, and we get some height out. How do we use Broyden's method? Well, the answer is that when we take the gradient of this function, it's going to have partial derivatives with respect to x and to y, and those partial derivatives, well, there will be two of them, and so those partial derivatives are a vector valued function. Each one of them will take in both x and y, and so we've got a little system of equations there that the partial derivatives are. And so when we shove them into our Broyden's method, they're a system of equations. We can generate the Jacobian for that system of equations, and we'll be good to go. So let's get our gradient. So we've already, let me shift enter this just in case I haven't. We've got our function, let's get our gradient. So I'll call it Rosengrad, which sounds, I don't know, vaguely Russian. Anyway, Jack's gradient. Jack's gradient of Rosenbrock. All right. So that'll get us a a function that is the partial derivatives of the Rosenbrock function. All well and good. Now, can we just, oh no. So that's the first thing. If we come back up here and look at the inputs that we set this to have, the only two that we have to put in, everything else there's some default. The two that we need to put in are the function, which we've got now, the gradient of the Rosenbrock function, and an initial guess. And in the spirit of testing ourselves, let's pick an initial guess that's far away from, you know, we could go to 1.1, 1.1, but let's go way up on this hill. Let's say 0 and 2.5. That's pretty far away. And you know, I won't be super mean to myself and start here, because then we'd have to go down and work our way around. You can see that there are certain places that converge more naturally to where the minimum is. But so yeah, so let's start it. Which number was which now? Yeah, so let's start at x is equal to 0 and y is equal to 2.5. And oh, that was the wrong one. Okay. So we need our initial guess, and this is where it's very important to remember that our initial guess needs to be floats and not ints. All right, so just like with NumPy, we do NP array. Here in Jack's NumPy, we do JNP array, and let's see. Yes, it was 0 and 2.5, and I did exactly what I said I wasn't going to do. I made that an int, but I caught it in time, and no syntax problems there. And now, fingers crossed, we can plug these things into our Broyden function. So yeah, let's do that. Broyden, and we'll plug in Rosengrad and x1. All right, there we go. Fingers crossed. What was our default? Max iterations is 500. If it doesn't converge within 500, that's not a bad sign. Well, it could be a bad sign, but if it doesn't converge in 500, we'll just ramp it up a bit. Okay, and the race is off. Interesting. That was 9. And where did we? Oh, because remember I set the range here to be 10. But let's just take a look and make sure everything makes sense. You know what? Let's print the norm too, so we can that'll give us an easy measure of if things are really going down or not. If we're getting closer to the place where f is equal to 0. Copy, and we'll say norm, and then paste that, and then there we go. I think that's everything we need. Let's run this again, and let's run our function. Oh, that's quick. Okay, so here's our norm. Whoa, okay, so our norm's hopping around a little bit. We start fairly close, and we quickly go very far away. Then we come back. Wow, we're really bopping around here. Just brief adventures into the stratosphere. And let's also look at our function values. Again, we'll don't worry, we'll run this a lot more, but so we're starting off like in the 2 and we've been pretty small there. Well, that makes sense because we started out and how is our function changing? It's also blowing up momentarily and then getting small. Okay. All right, well, let's run the wheels off this thing. So we'll go to range max. And let's run. That's why I thought I was like, wow, it really went through 500 iterations fast. Well, no, it went through 10 iterations. And let's see, 400. So after 499 iterations, we're not particularly close. If I recall, this is x, this is f. We are, I mean, we're kind of close to 1, 1, but our function really is not close to our function is not close to where we want to be. So let's run it for more iterations. Now, I could be measured. I could just go up to 1,000. You might ask me, why am I changing that number rather than changing it in the function? And I don't have a good answer for you. Might have a minute here. Our norm is small. That's promising. Sometimes it seems to be noodling around a bit. It's not crazy. We're kind of in the right neighborhood. Let's you know what? Let's keep. Well, actually, so I mentioned before there were two reasons we were using Jackson again. After this batch, we'll implement that other reason. That's just-in-time compilation. Huge speed up. Let's see where we end up. Okay, there we go. All right, so we never quite made our criteria, it looks like. So we were almost there. We were in the right neighborhood, but not for very long. Wow, only lost very few iterations that it converged. It's kind of lucky. Wow. All right. But this will be a good demonstration because that, I don't know. You can time and see how long that was. I don't know if that was 20 seconds, 30 seconds. We'll see what the difference in speed is. So the thing that we're just-in-time compile is our function, our Rosenbrock gradient. We're going to go JAX. JIT stands for just-in-time compilation, and let's run this. We'll see how long it takes. It feels faster, but is it? Okay, 2,000 and interesting. We didn't converge that time. That's interesting. Okay, well let's really run. I don't know if that's in rounding error. I wonder why that is. Why is why is there variation? It's interesting. Something for you computer scientists out there. If you're watching this, maybe for kicks and giggles, since I'm a newbie here. Yeah, that's J inverse. All right, we're well away from 0. That's so interesting. Okay, all right. Well, and if it makes it here after 4,000 iterations, I'll call it good. I suppose we don't need to be watching this every time, but it does kind of, it tells us that the computer's doing something. There's a certain excitement in that. Okay, so our norm's kind of small. We'll see if it stays. There we go. Okay, so right around 3,500, we got to what? How long? Not long. Again, and just in the last few. But again, that's probably why it did before. Okay, so that's Broyden's method. Let's see how far in are we? 40 minutes. Okay. Yeah, that's about right. All right. So that's our basic Broyden's method. Now last time we also talked about constraints. All right, and we talked about Lagrange multipliers as a way to do that. Let's get rid of this, but I do want to make it not take up all this space. So I'll set verbose equal to false. Also, let's see if it really keywords are capital. Pardon me, someone came in for a moment. Okay, so okay, there we go. So yeah, when it doesn't have to print everything out, it's like lightning. Let's see, yeah, but it still took 3,500 iterations. That is something. Okay, so Lagrange multipliers. As a reminder, we had a, let's open OneNote. As a reminder, we had some topological surface. We have some surface, and there's some maximum or minimum on that surface. And if we were just to march up that surface, we'd be going in the direction of the gradient, which is the direction of steepest ascent. And because when you compute the gradient, it automatically points in the direction of steepest ascent. And we keep going until at last we arrived at our optimum. And the idea of the Lagrange multiplier is that there's some constraining line that we have to be on, or some constraining section of space, but we'll just start with a constraining line. There's some constraining line that we have to be on, and that line has some equation. We'll call it f of, we're already using f for this function over here. We'll call it I'll call it h of x and y is equal to 0. And if you want something more thorough than what I'm about to do, the last 13 minutes of the previous video or thereabouts are devoted to this topic. So this line is some function of x and y, and it's equal to 0. And we can always make it to 0 because if it's equal to something else, we can just move that term to the other side, and then this equation will be equal to 0. So we've got this as our condition that we've got to meet, representing some line. And Lagrange's idea was that this line is one instance of a whole surface. So there could be a some hx of x and y equal to I don't know, 4, or equal to 20. And what that means, relevant to these lines, is there are other lines that are part of the same family of curves, and they make their own in this instance 3D surface. And so yes, this line is one family of lines, and that together make a surface. And if you were to take the gradient of this function, if you were to take the gradient of, actually, you know what? It would be more proper to call this function g. G h representing the specific instance where all this stuff is equal to 0, and g representing the more broad family of curves. So the gradient of this surface is going to point, it's going to be orthogonal to this line at any point. So if we were to calculate the gradient a bunch of times, you know, wherever on the line we are, the gradient is going to be orthogonal to it, because you can kind of see visually this is the direction that that it would go to ascend. And if we happen to calculate the gradient, the whole idea of this constraint is we're looking for the maximum point that of this function along this line, and that looks like it would be right here. You know, if this is the maximum or minimum, if this is the most extreme point, this is the point here on our constraining line that touches the highest or lowest elevation. So if we were to calculate the gradient right here, it would point in that direction. And if we were to calculate the gradient, that's the gradient of g or of h. And if we were to calculate the gradient of our actual function that we're looking at, that's going to point directly opposite. Pardon my kind of wiggly drawing. And you know, as we go up further, that line is going to turn. But right here at this point, it's orthogonal to the contour line, as I've drawn it. Don't get too hung up on my sometimes unfortunate drawings. But so this was kind of the key insight behind Lagrange multipliers. These two gradients are going to be collinear. I said orthogonal, didn't I? They're not going to be orthogonal. They're going to be collinear. They'll either be they'll be perfectly parallel, and well, they'll be collinear. This depending on what this line is, they might even be pointing in the same direction. The way in which they'll be different is likely their magnitudes, and that's the actual Lagrange multiplier. Lagrange said whatever the gradient of this function, of our function f, I'll label this. This is f here, this surface. The gradient of our function f is about the same size as the gradient of our constraint surface, as long as we multiply it by some constant. This constant can, and then you know we subtract one from the other. If this is true, if they really are the same size, then these things will equal 0. So that's the condition spelled out by this maximum point. And so that's the core intuition behind this Lagrange multiplier. And the way we translate that a little bit further into math is Lagrange invented, you know, or described the Lagrangian, which is these two functions together, f minus lambda g. And if we take the derivative, or if we take the gradient of the Lagrangian, gradient of L, that's, you know, h and g, or f and g are both functions of x and y. So when we take the gradient of L, we're taking it with respect to x and y. That's equal to the partial derivative of L with respect to x, and the partial derivative of L with respect to y. And we say that both of these things are equal. Both of these things are equal to 0. And when we say that, you know, imagine that we took the partial derivatives of L with respect to x and y. We take it with we take the partial derivatives of L with respect to x. We get some partial derivative component of f, and a partial derivative component of g, both with respect to x. When we set that partial derivative equal to 0, we're saying that these two partial derivatives together are the same magnitude and pointing in the same direction, again, when g is multiplied by lambda. And the same thing for y. If the partial derivatives are equal in magnitude, that means they're equal in magnitude, equal in direction, that means they're collinear. So that's this condition here, but we don't want to forget about this condition here. And all that is to say is, that we actually do want to be on this line, because there are plenty of lines that would have a gradient at some point that is collinear with this line. We won't, with collinear with our function at this maximum point. We want to make sure that we are on this specific line, and so the way we do that is we say partial L partial lambda is equal to 0. There we go. Partial L partial lambda is equal to 0. And if that's the case, what does that mean? Well, if we take the derivative of L with respect to lambda, we get g. So we're saying that g is equal to 0. And if g is equal to 0, then it's h. We're at this condition. So all these conditions, all these things together, spell out, well, really these three equations: partial L, partial x, partial L, partial y being equal to 0, and partial L, partial lambda being equal to 0. These specify what we need to know for our Lagrange multiplier situation. Okay, so let's get a constraint. We'll define a new function that will be our h, or our g, really, and we'll call it we'll just spell it all the way out: constraint. And constraint will be just like Rosengrad here, and whatever function. It'll be a function of our input vector x. Actually, let's do input like we did before. Okay, and we'll say this input. And so, what constraint? Let's have a linear constraint. So we'll return. So if we were to remember, I was saying before, if we have some equation that's not equal to 0, we can just bring the right side over to the left side, and suddenly we've got an equation that's equal to 0. So if we had the equation y is equal to 2x minus 1, y is equal to 2x minus 1. Well, if we had that equation, we just bring these things over to the other side. Minus 2x plus 1. And now we've got something that we will make sure this function ends up getting set equal to 0. And let's see. So there's our constraint. And let's make sure there's no... Oh, there's always something. Oh, yeah. Can't just write 2x. What does that mean in Python? Nothing. Okay, so we've got our constraint. Let's get our Lagrangian going. So let's define a Lagrangian too. We'll just call it L Lagrangian. Lagrangian would be a function of x. And so we want the point on our Rosenbrock surface that also meets this constraint. We want the lowest point on our Rosenbrock surface that meets this condition of this equaling 0. So our Lagrangian is going to equal our two functions together, just like we said back here. It's going to be f minus lambda g. And we'll need to add a lambda index to our input our input vector. Well, we'll do that in just a minute. So L is equal to our Rosenbrock, or Rosengrad in this case, Rosengrad of x minus lambda, and we'll say lambda is x, our third index, x, which without that'll be our lambda parameter, times our times our constraint function. Constraint x. Is that right? Because we are not using Rosenbrock, we're using our gradients here. No. Okay. We want this to be Rosenbrock, I think. Rosenbrock. Because we're going to take, I guess I can just return this value. I don't need to give it a name. Return Rosenbrock. So there's our lambda. And now we want the gradient of this thing. And that's the function that we're going to enter into. That's the function that we're going to enter into our Broyden's method. And once we've done this, we'll take a look at that surface and make sure that this minimum that we've set makes sense. So dl, dl, we don't need to. This isn't a function in the same way that these others. dl is Jax dot gradient of L. Simple enough. Or an that colon. Okay, so we've got a dl. So that's our function. We need a starting guess vector. See? So, and we need to add some starting guess for L. I'll just say 1.0. Okay, and just like that, let's call this some other. We'll call this x2. Now we have again the things that we need to run our Broyden's method. Okay, so we want dl. That's our function that we're going to plug in, and x2 is our constraint function. Well, it's our initial guess, not our constraint function. I should have set verbose to false. How are we doing? Oh, function's getting pretty small. Didn't quite get to the convergence point. Oh, wait. Oh, did we? Yes. Yes, we. Looks like we did. So, just to recap. Wait, does our minimum point lie on that constraint? I suppose I should know. Oh, yes it does. So, if y is 1 and x is 1, then this whole thing should evaluate to 0 right at our minimum. So we did find, I should have known that already, but we did find our minimum. That's great. And that took us fewer iterations, and that makes sense because we're only searching on a line, not having to search the whole surface and go every which way. Okay, so that is our constraint. That is our equality constraint. Just for kicks, I do want to see how fast this evaluates when we don't have to print everything out. False. How long does it take? Still a decent little bit of time. Oh, but I didn't do just-in-time compilation. you know what, I do want to see Jack's JIT just-in-time compilation, because it really is an amazing difference. That was maybe 8 to 10 seconds. Oh my gosh. Okay, so just remember how much of a difference that makes. So that was an equality constraint. Call this equality constraint. Single equality constraint. We could have multiple equality constraints, although I guess if we're just looking on two lines, you know, there's going to be one place where those lines meet. But maybe we have a, you know, it has to be on a plane or something. But we can also have an inequality constraint. And that inequality constraint is, yes, that inequality constraint. Okay, let's label this inequality constraint. Inequality constraint. Well, and what I mean by that is, you know, before we were, you know, let's see, the function was y is equal to 2x minus 1. So when x is 0, y is minus 1. So y is around here. And when, well, anyway, we've got a line going across, and so the equality constraint means we have to be on that line. The inequality constraint means we have to be on one side of that line. And yeah, so we'll do that next. So our inequality constraint. Let's define. Let's define our inequality constraint. I'll call it inec. And I'm going to define another variable, which I'll call slack. I'll call slack input 3. No, input 2. And I'll shift lambda up to be 3. And so the way this works is that we give a whole nother variable that lets us search everything to the north of or south, whatever, east or west of our line, and we let that vary. And the way that we keep it on one side is we square it. We go slack squared, and if we wanted to stay beneath it, we would make this a negative sign. But let's stay above it, and so there we go. Here's our inequality. And this would be equivalent to saying that y has to be greater than or equal to 2x minus 1. If we were to rearrange things, you know, we're saying we have y is equal to 2x minus 1, but then in addition to y, we have this slack variable. All right, so that's our inequality constraint. Pretty straightforward. And let's get some of this good stuff. Again, let's define another Lagrangian. We'll call this no, we need to define L2. And again, it's a function of our input vector, and we are going to be using a lot of the same stuff. The only difference is, like I said, I'm shifting lambda up. I'm going to make lambda the third variable in our input vector. And so yeah, we've got four vectors. Let's get our gradient. Jax.grad. Boy, let's make life easy. Isn't Jax wonderful? Jax.grad of L2. And you know, we don't have all night. Let's Jax.jit. We can just do just-in-time compilation right from the beginning. And let's get an initial guess vector. I'll keep lambda as 1. And we can have our slack variable be 1 to start as well. And just like that, we've got pretty much everything we need. DLX3 and DL2. And this the first time we run it. Let's see what's going on. True. Oh, something happened. We got a whole lot of not a number. Hold up. What happened? What's going on here? Something funny is happening. String output truncated with the last 5,000 notes. What in the world? Huh. Interesting. Did I change anything? Oh, muy curioso. Are you ready for the mistake? Ugh. Okay, so here's my L2. Here's my inequality constraint. I didn't change the name. Oh, the dangers of copy-paste inequality. It wouldn't be a real coding video if there weren't some little dumb thing like that. Okay, so now that we've got that sorted out, no wonder the derivatives were evaluating to not a number, because it's not a function of those derivatives. The constraint function here is purely not a function of that third derivative, of that new value, the slack value. Okay, now let's send our max iterations to be something fun. I don't know, 2,000. And let's turn our verbosity off. We've seen these printouts happen enough. False. Oh my gosh. And just like that, we get to 2,000. So what did we end up evaluating to? We got pretty close to 1. We're not quite there, but we're close. And there's our F values, and we're getting close towards 0. We're in the neighborhood. We could let it. We could bump it up 500, say. But I think we get there. Really, didn't converge very much, but let's go whole hog. What's going on here? Seems like it's giving me the same numbers every time. I might want to restart the runtime. Something funny is happening. That's my equality constraint. Here's my inequality constraint. Okay. This whole thing is... Yeah, let's restart the runtime just in case. Restart runtime, yes. And we don't need this jazz anymore. We can get rid of that stuff. Let's just try everything. Oh, well. Okay. Well, that's still converging. That's good to know. Here's our equality constraint. That's converging beautifully. And back to inequality land. Let's take the max iterations off here. Let it run to 4,000 if it needs to. Oh, it just hadn't finished running yet. No. Huh. Huh. Staying small. Is this more difficult for it than the regular thing? Oh, let's... I don't know. Do we really want to go above 4,000? That's it. 7,000? I don't know. Really strange. Okay, well, after a little bit of experimentation, I brought in the vector from the example that I was sort of working off on when I was trying to understand this, and it doesn't fare much better. Well, no, I guess it does fare much better. No, I'm getting ahead of myself. So if I leave the inequality constraint as it is, passing right through the minimum, then I get performance like this, where I'm fairly close to 1, but not there in the same way. If I shift the inequality constraint ever so slightly, just barely off that line, 0.99, I get very fast convergence to that same high degree that we've become accustomed to earlier in the video. Why there should be such difficulty, I'm honestly not sure. I don't know how close we can get and still see there again. We're not passing through the line. We're barely on it. So removing the slack variable makes this very fast and easy and highly convergent, and varying our equation ever so slightly. You know what? Let's try, instead of squaring it, let's make our slack variable absolute value. We'll go JNP and ABS. Let's see if that makes it converge more quickly. Let's put this back to 1. Well, this is a total experiment. I have no idea if this will help at all. It did not help. Okay. Huh. I'm just trying stuff at this point. I mean, it's kind of good enough, but you know, for a lot of problems, not really. There are many problems where we want to be at that. Oh, okay. Interesting. So by raising it to the 4th power, which still keeps it positive everywhere, we get the kind of convergence that we're used to seeing. Why this works, I have no idea. I'll be very, very honest. Yeah, so if you're watching and you have some idea, go ahead and post it in the comments, or even if you just want to speculate. Obviously, this increases the derivative. No, it wouldn't increase the derivative, because our gradient is the derivative of let's see. Well, let's look at our components. So our components are the inequality, which is now highly dependent on the slack variable, and the Rosenbrock, which isn't dependent on it at all. So we've effectively increased the responsiveness of our inequality constraint to small changes in the slack variable. Somehow, maybe, that has, clearly raising it to the fourth power, that did the trick. So maybe it just wasn't moving quickly enough before relative to some of the other, but it was already squared, which is more than, well, I guess it was squared. If we look at the Rosenbrock function, we've got x to the fourth power and we've got y squared. I don't know. A bit of a mystery. Okay, well at this point, we've touched everything that I wanted to look at in this video. We've dealt with the general, well, we've dealt with sort of the vanilla Broyden's method, and we've added on to it equality constraints and inequality constraints. Did have this unusual. I do want to see if it will converge for that other x. Is this just something specific to this particular point? Really poor convergence. Well, at this point, I think this may be the subject for another video. Why it converges at some point and then doesn't converge at other points. I know that's a science in and of itself. Well, I guess if there's a lesson to take from this, from the point of view of a numerical methods newbie, or maybe someday a numerical methods journeyman, is barring some error in my code, it's important to seed your algorithm with multiple starting points, because some of them, at least in this example, some of them converged quite handily and some of them didn't. And I think that's what I'll take going forward. All right, thanks for watching. See you next time.